We've learned that when a chemical reaction occurs in a sealed container under conditions of constant volume, the energy begins to evolve only as heat, taking work out of it, since when volume is constant, work is constant, because work is equal to the external pressure and change in volume. When a chemical reaction is open to the atmosphere under conditions of constant pressure, for example, if you have a gas stove and you light it, that is under constant pressure because it's out in the atmosphere, there's nothing containing it, the energy can evolve both as heat and work. We know that the change in energy of the reaction is the measure of the total energy change plus both heat and work. We've learned delta E is equal to Q plus W. Now, when we burn natural gas on a stove, we don't really care about how much work the combustion reaction does on the atmosphere, expanding it. We really only care about making sure that our food gets heated and how much heat that it needs to make the time go by a little bit faster. So looking at that condition, that's something called enthalpy, when we're not looking at the work and we're just putting a situation under constant pressure and looking at the amount of heat flow. So enthalpy of a system is the sum of its internal energy and the products of its pressure and its volume. Now this can go a little bit deeper. Since we know that internal energy is a state function, we care about its final and initial conditions as well as pressure and volume. Enthalpy is also a state function, so we're interested in the change. Not just H, we're always interested in delta H because it's a state function. So under constant pressure, if we rearrange this equation now, adding our changes in there, we already know that some of these we can define. We know that under constant pressure, we can define the change in internal energy under the following. I can say that the change in internal energy is my Q with a little sub P, meaning constant pressure, plus work. And I know that the definition of work is when the system is doing work, I have pressure external times a change in volume. The usual equation for work is the external pressure having the negative sign times a change in volume. All we did here was move this negative sign over. Now you can see that this can be substituted in for your energy, and this can be substituted in for your P delta V, which then will give you a new equation. So then you have that change in enthalpy is equal to heat plus work, and then W. Now these W's are going to cancel, and therefore your change in enthalpy is the flow of the energy at constant pressure. Enthalpy and internal energy both represent changes in a state function for the system. Internal energy is a measure of all of the energy, heat, and work exchanged with the surroundings. Now again, if you are at constant volume, you have no work and you're looking at the energy flow specifically from heat. Enthalpy, therefore, is a measure of only the heat exchange under conditions of constant pressure. When you're looking at enthalpy, you're not looking at the work. When you have a positive and a negative amount of enthalpy, there are two new terms that we associate that with. For example, a positive enthalpy indicates that heat flows into the system as the reaction occurs. Endothermic, it absorbs heat. The opposite of that is when it's negative, it's releasing heat, that's exothermic. Now if we take a moment and look at these examples, sweat evaporating from the skin. The sweat is your system, and in order for sweat to come out of your skin, it has to absorb energy, so this would be endo. Water freezing in a freezer is exo. It releases heat to begin to freeze. And wood burning in a fire needs heat to be absorbed to burn, so it's endothermic. Now, stoichiometry involving enthalpy. When you have a reaction, the enthalpy change for a chemical reaction is defined as delta AHrxn, or heat of a reaction. It can be called both. Since we know that at constant pressure, we look at enthalpy as heat. We can also call it heat of the reaction. This depends on the amount of material undergoing the reaction. The amount of heat generated or absorbed when a chemical reaction occurs depends on the amount of reactants that actually react. The less, the more is going to change that amount of heat. The magnitude of the heat of the reaction reflects the stoichiometric amounts of the reactants and the products for the reaction as written. What that means is, take a look at this reaction right here. I have propane reacting with oxygen to create carbon dioxide and water, and there's a heat of a reaction of negative 2,044 kilojoules. This means that there's 2,044 kilojoules per 1 mole of propane, or negative 2,044 kilojoules per 5 moles of O2, and that can continue on. So that heat of a reaction represents the individual stoichiometric amounts of the reactants and the products. Let's put that into practice. So if we look at this question right here, nitromethane burns in air to produce significant amounts of heat. We have our reaction, it's already balanced, and we have the heat of reaction given. How much heat is produced by the complete reactions of 5.5 kilograms of nitromethane? Okay, well, I know that my heat of reaction represents my Q over my amount of moles, the amount of the reactants. So I'm going to specify that, and I know that I have negative 1,418 kilojoules over, since I'm looking at nitromethane, 2 moles CH3NO2. So I want how much heat. That means I want to get rid of the moles. So I just want kilojoules here by itself. And I'm giving my mass. So I have to take my 5.56 kilograms and convert to moles so that I can then cancel out the moles. So first, there's 1,000 grams in 1 kilogram. And then my molar mass is 61.021 grams. And since I want to have moles so I can cancel, I'm going to put it on the top, 1 mole over 61.021 grams. And then I can use my heat. And then double check, does everything cancel? Kilograms go away, grams go away, moles go away. You can always rearrange this too, since you just want heat, and you'll see that to get the heat, you need to figure out the difference here and cancel out the moles. So that's going to end up giving you a value of negative 6.49 times 10 to the power of 4 kilojoules. Now let's look at a little bit of a different problem. Using this combustion reaction, and this should also be propane, creating negative 2,044 kilojoules, if a pork roast absorbs 1.6 times 10 to the third kilojoules to fully cook, and if only 10% of heat produced is actually absorbed by the roast, what mass of carbon dioxide is emitted in the atmosphere during grilling of the pork roast? So basically, when you're burning that pork roast, you're using propane gas, right? So on your stove or whatever you're using, that's all propane gas, like on a barbecue. So this is the initial amounts that you have. And you want this. So first thing that I realized is I'm going to need to use mole ratio eventually. And if I need to use mole ratio, I need to find moles of propane to then go to moles of carbon dioxide, to then go to the mass, since I want to end with grams. So basically, I'm going to have to use my information given here to figure out exactly how many moles I have. Well, I'm told that I have 10% of heat produced. I'm going to abbreviate Q for heat. That's absorbed by the pork. I know total heat here. So I'm going to take my 10% and multiply by my amount of heat. Which then gives me 220.4. Note how I didn't make this negative because it's the amount being absorbed, not the amount being released. Because the pork absorbed actually this much. Now it wants 1.6. So we know that to fully cook, it needed 1.6 times 10 to the third kilojoules. So to get the moles now, we want to isolate. Now since this came from reaction, this is also written as 2000 and 2004.4. So this would be written 204.4 kilojoules over the amount of moles of propane, which is only 1. So I didn't change anything. I still used my 10%. I just had a quick typo there. So 0.10 times 2044 gives you 204.4 kilojoules. That's for the overall reaction. I'm looking at just my propane, so I put 204.4 kilojoules over 1 mole of propane. Now I want moles of propane. So then what I'm going to do is multiply the amount of energy that I actually needed and divide it by the heat of the reaction for the propane to get moles of propane by itself. Because then you see kilojoules and kilojoules cancel out, and then if you plug that into your calculator, you should get 1.6 times 10 to the third divided by 204. 7.83 moles. Now you have your amount of propane and you want carbon dioxide. So now that you have moles, you can use mole ratio. So there's 3 moles of carbon dioxide for 1 mole of propane. And since you want mass, you have one more step and you use your molar mass. And that gives you an answer of 1,033 grams. And we have 2 significant figures. So I would say 1.0 times 10 to the third grams of carbon dioxide. And then you're done. So it's always important to know this is always per moles. And this was just in kilojoules. It was just the amount of heat that you needed. So we used those amounts for propane to find the moles of propane, and then it was just stoichiometry and molar mass to get the amount of carbon dioxide. So now talking about how to measure that. So we know we can measure internal energy as a heat when putting a reaction under the conditions of constant volume. Now, a little bit more of a experiment ability to do on your own is through something called coffee cup calorimetry. For many aqueous reactions, we can measure the heat of the reaction using coffee cup calorimeter. Two styrofoam cups are placed together, one in the other, creating insulation. The calorimeter is equipped with a thermometer and a stirrer. The reaction occurs in a specifically measured quantity of a solution within the calorimeter. During the reaction, the heat evolved causes a temperature change in the solution. You'll have an initial temperature when you then create the reaction by adding the other aqueous solution to the one in the cup. The temperature will rise. If we know the specific heat capacity of the solution, we can calculate the heat of the solution in the calorimeter. Therefore, heat of solution is equal to MCAT, the mass of the solution times the specific heat of the solution times a change in temperature, which then tells us that the heat of the reaction is equal to the heat of the solution. We always have to remember that according to the law of conservation of energy, the total energy is constant. So the energy of the system has to equal the energy of the surroundings, here being the reaction in the solution, one absorbing and one releasing. The insulated calorimeter prevents heat from escaping. So we assume that the heat gained by the solution equals that lost by the reaction. Because the reaction happens under conditions of constant pressure, the heat of the reaction is equal to the delta H, the change in enthalpy of the reaction. This measured quantity is the heat of reaction for the specific amount of reactants that react. To find the enthalpy of the reaction per mole of a particular reactant, we would then divide it by however many moles of what we're actually looking for. So putting that into practice, zinc reacting with hydrochloric acid forms zinc chloride and hydrogen gas. When 0.103 grams of zinc is combined with enough hydrochloric acid to make 50 milliliter solution in a coffee cup calorimeter, all of the zinc, raising the temperature of the solution, reacts, causing this temperature change from 22.5 degrees Celsius to 23.7. I lost my slide there for a second. There we are. Find the enthalpy of the reaction. Use this density and this specific heat. So if I want enthalpy of reaction, I'm going to start right there. If I want this, I want joules or kilojoules per mole. So that's kind of my ending unit. For me, sometimes that helps so that I can piece together exactly my units the way that I want. So I know I'm in a calorimeter and I can find my heat of my solution using MCAT. Now my M, I will have to find from using the density and the volume. So 50 milliliters times 1 gram per milliliter will just give you wouldn't even need to write this, but 50 grams. You just plug everything else in, you have 50 grams times 4.18 joules per gram Celsius times your temperature change. And that gives you your heat of solution is equal to 250.8 joules. Since heat solution is equal to heat of reaction, your heat of reaction is 250.8 joules as well, negative. So the negative sign here doesn't essentially matter too much as long as you know that the reaction released heat in order for the solution to absorb and form, and that the magnitude never changes. So now you have joules. You, however, want joules per mole, and you're given mass of zinc. The reason we didn't use the mass of zinc when we were looking for the solution is because this is the solution, right? This is what happened afterwards. The zinc and the hydrochloric acid, you don't have anymore to associate that with the temperature change. So we needed to use the amount from the solution to figure out the heat. Now, we still have to incorporate the amount of zinc. So, a couple ways to do this. You can just isolate the moles and then divide, or use it all in one equation. So your amount right here, negative 250.8 joules, represents that amount of heat that was released for 0.103 grams of zinc. Now we want to get that per mole, so then you can multiply it by its molar mass. And the molar mass of zinc is 65.39, which then will give you negative 1.60 times 10 to the 5th joules per mole. And that's how you do that, knowing that you find the heat of the solution. So if you're looking at the reaction, you're still looking at the reactants and those specific amounts. And that enthalpy is always looking per mole, per amount. Relationships involving the heat of the reaction. The change in enthalpy for a reaction is always associated with a particular reaction. So for example, if you have this reaction and then you multiplied it by 2, you have to multiply your heat also by 2. Or if you flip this reaction here was flipped to go here, you have to change the sign. If you're manipulating one reaction, you have to also manipulate the heat of the reaction. This brings us up to Hess's law, meaning that the sum of all the reactions that you need to get an overall equation that you have will equal the heat and enthalpy change of the overall reaction. The chemical reaction equation can be expressed as a sum of a series of steps. Then the heat of the reaction for the overall equation is this sum. What that basically means is that if you have this equation and you don't know the heat of the reaction, but there's small little reactions where the heat of the reaction is known, you can manipulate to get your overall equation, and the sum of all of those heats of reactions multiplied and divided or manipulated however you did to the reactions themselves will equal the heat of the reaction that you're looking for. Let's put that into an example. So I want this right here, this equation. And I'm given my equation 1, 2, and 3. I'm sorry that this cut off here. This delta H is equal to negative 255 kilojoules. So I can see that I want to manipulate this to get exactly what I want. Well, I have 3 NO2s on my left side, and looking at my equations, I'm going to rewrite them so it's a little bit easier to see. I have 2NO plus O2 makes 2NO2. Then I have 2N2 plus 5O2 plus 2H2O. And then N2 plus O2 makes 2NO. Okay, so the only reaction from 1, 2, and 3 that has NO2 is this one. So what I'm going to do is I'm going to flip this reaction because I want NO2 on my reactant side. Also, because it's the only one that gives me my NO2, I want 3 NO2. So I need to figure out what I can do to 2 moles of NO2 to get 3. That's multiplying by 1/2. So I'm going to multiply by 1/2 and flip. So I get 3 NO2 makes 3 NO plus 1.5 O2. And then my delta H becomes positive 173, and I have to multiply it by 1.5, which gives me 259.5. So now I do my next one. I'm going to leave the color. I'll change it. The next one I have, okay, I just figured out this part. What about water? Well, I have 2 waters here, and that's my only equation that gives me water, so I have to get rid of it. It's on the reactant side, so I don't need to worry about flipping it or anything because it's already on the left side of the arrow here. and it's on the left side of the arrow of what I want. But there's 2 and I only want 1. In order to get 2, I will have to divide the whole equation by 1/2, which will give me N2 plus 5 divided by 2. I'm going to leave it as a decimal. You can always leave it as a fraction. It's 2.502 plus 1 water makes 2 HNO3. And then I have to also do that with the enthalpy. So then the enthalpy will be negative 255 divided by 2, which is negative 127.5. So then last one. I just figured out my water and my nitric acid. I have now 2 nitric acids. Now I am looking at NO. Now NO shows up twice. I have NO right here, and then I have NO right here. So right now it's on both of the product side, and I need to get rid of it. If I leave it on the right side of both equations, that's adding. To get just one NO on the product side, I'll have to subtract. So I flip the reaction. So I get 2NO makes N2 plus O2. Now, all of this will then should give me my overall reaction. But I also have to remember to change the sign of my delta H to negative 181. So now let's see what cancels out. So I have 3NO2 nowhere else. So I left with 3NO2 plus, so I just dealt with that. Then I have N2 here and N2 here, so that cancels out, no more of those. I have 1.5 oxygen on the product side and 1 here, which is 2.5 minus the 2.5 from the reactant side, so that goes away as well. Then I have my 1 water, so that's gone. And then I'm here, getting a little tricky. And then I have my 2HNO3. So that's gone. And then I have my NO, 3 minus 2, which is 1. So then I have 1 NO. And then if you look, this is exactly equal to the one on the top. So you're done. So then your overall delta H will be the sum of all of them, which is negative 49 kilojoules. Last little bit is looking at standard enthalpies of formation. So basically, experiments have been done to figure out the standards of all of the different enthalpies, but some are defined in their pure form. Enthalpy is a change of heat in a chemical reaction. Since we are interested in the change in enthalpy and not in the absolute values of enthalpy itself, we are free to define 0 of enthalpy as conveniently as possible. When climbing a mountain and change in altitude, looking at a change in enthalpy is like an absolute quantity, where the altitude itself is the enthalpy, and that's a relative quantity defined to some standard. It could be like sea level. So we define standard state in different ways. So for a gas, the pure gas at a pressure of exactly 1 atmosphere, we define that as 0. For liquids and solids, those pure at 1 atmosphere and a temperature of interest have certain standard states, and for a substance in solution of 1 molarity. So these are all defined at these pure states. The standard enthalpy change is a change in enthalpy for a process when all reactants and products are in their standard states. Standard enthalpy of formation is those standards for the pure states of different compounds. So for a compound, they change in enthalpy when 1 mole of the compound forms from its constituent elements in their standard states. For a pure element, it's just 0. So for a compound, the heat of formation depends on the sum of all of the elements that it's made up of. And for an element, it's 0, because that's its pure form. So elements to compounds give off our heat of formation, and the reverse of that will be the inverse of heat of formation. So for example, here you can see to produce methane, the heat of the reaction was unknown, but then some of the constituent reactions was figured out. So the way to figure out a heat of a reaction is to use the sum of the heat of products minus the sum of the heat of reactants. Looking at a little practice, so here we have these standard enthalpies, and it says use the standard enthalpies of formation to calculate the enthalpy for a reaction. So we need to figure out the heat of formations for all of these. So either that would be given to you or you would have to look it up. We know that the overall equation is so the heat of formation for Cr2O3 chromium 3 oxide is negative 1139.7 kilojoules per mole. For carbon monoxide is negative 110.5 kilojoules per mole. Chromium, that's a pure element, is 0. And carbon dioxide is negative 393.15 kilojoules per mole. So you then plug everything in using the coefficients. So products minus reactants. So you're looking at chromium. So you have 2 times 0 because chromium was 0 plus 3 times negative 393.15 kilojoules per mole. That gets subtracted from the sum of the reactants, which is 3 moles times negative 110.5 kilojoules per mole plus 1 mole times negative 1,139.7 kilojoules per mole. And then you sum all of that together, and that will give you 290.7 kilojoules. So know that sometimes you may not be given one of the amounts, and you'd be given your heat of your reaction, and then you just solve for it that way. And that's all thermochemistry.